fantastic presentations. And without further ado, I will introduce the first speaker, who will be Dr. Bhavani Thuraisingham. Is that the correct pronunciation?
Yes.
Yes, thank you. I was so afraid it wasn't. Okay, so Dr. Bhavani is the Founders Chair Professor of Computer Science and the Executive Director of Cybersecurity Research and Education Institute at the University of Texas at Dallas. She is a visiting Senior Research Fellow at King's College, University of London, and an elected Fellow of ACM IEEE AAS, the NAI, and the BCS. Her research interests are on integrating cybersecurity and artificial intelligence, also known as data science, for the past 35 years. She has received numerous awards, including with the most recent ones being the IEEE CS Services Computing 2017 Research Innovation Award, the ACM CODA SPY 2017 Lasting Research Award, the IEEE ISI 2010 Research Leadership Award, the 2017, so numerous awards. This is a lot of distinguished kind of contributions. So, but nevertheless, also she has co-chaired the Women in Cybersecurity Conference in 2016 and delivered the featured address at the 2018 Women in Data Science at Stanford University, where she serves as the co-director of both the Women in Cybersecurity and Women in Data Science centers at the UT Dallas. Her 40-year career includes industry, working on Honeywell, Federal Research Laboratory, MITRE, US government, NSF, and US academia. Her work has resulted in more than 130 journal publications, over 300 conference papers, 150 plus keynote and feature addresses, 6 US patents, 15 books, as well as technology transfer and research to commercial products and operational system. She received her PhD at the University of Wales, Swansea at the UK, and the prestigious earned higher doctorate from the University of Bristol, also in the United Kingdom. So without further ado, welcome, Bhavani, and
thank you. Thank you so much, Dr. Tatskova. I just wanted to ask, sometimes early in the morning, there might be a network bandwidth problem. So if you can have my presentation ready so you can start playing just in case on your machine, is that possible?
Yeah, I can get it started.
No, what I'm saying, should we play? No, I like to give the presentation, but if we get stuck, then you can.
I understand. So okay, just
thank you so much.
Yeah, it will be ready.
Thank you very much, everyone, for inviting me, and I'm really honored to give this presentation, and really pleased to be here. IEEE ACM, Big Data Computing Applications and Technologies. And what I'm going to do is share my screen and okay. So let's see. So can you see my screen, the presentation?
Yes, we can see it.
Okay, so I just want to put the, okay. So my talk is going to be on integrating cybersecurity and data science / artificial intelligence with applications in Internet of Transportation and infrastructures. So it's going to be in 3 parts. The first part is integrating cybersecurity and data science. So I'm going to use the words data science, AI, machine learning sort of interchangeably. And so integrating in cybersecurity and AI, we call it SecAI. So there are going to be 4 key aspects here. One is big data security and privacy. And I'll give some context. And then some of our work on privacy-aware quantified self. And then data science, machine learning applied to cybersecurity. And one of the most important topics is emerging in cybersecurity is something that's called secure data science. What happens if the machine learning techniques are attacked? So that's going to be the first part. The second part is with some of the work that we did with one of our PhD students who graduated recently, and that's going to be cyber physical system, one example cyber physical system, which is security and privacy for the Internet of Transportation systems. And then the third part is applying part 1 to part 2. That is applying cybersecurity and data science, integration of that to the Internet of Transportation systems. I'd like to acknowledge all of our sponsors and my colleagues, Professor Alvaro Cardenas for our work on cyber physical system security, Murad Kantajulu for our work on attacks to machine learning techniques, Latifur Khan for our work on applying data science for cybersecurity applications, and then Dr. Raul Quinones was a former PhD student who did the work on secure cyber physical system, and our project coordinator, Ms. Rhonda Walls. Okay, integrating cybersecurity and data science. I want to give some background. So back in 1996, so that's almost 24 and a half years ago, I introduced the idea of the privacy violations that could occur due to data mining. And that was presented at the IFIP 11.3 conference in Como, Italy in 1996, and later at the Pacific Asia Knowledge Discovery Conference in Melbourne, Australia in 1998. And then I published, I call it a landmark paper. Reason is because I was a program director at the National Science Foundation, and I published this paper in 2002. So when you are a program director, that sort of, spawns a new area of research, and a lot of people pay attention to it, and the paper also gets citations. Okay, so then people at IBM Almaden Research Center, they came up with this whole notion of privacy preserving data mining or privacy aware data mining. So the goal is to have, the original goal is to add some noise. Okay, so original goal, you have the original data, you add some noise, and then you have the modified data, and then you do the modified data mining process, and the final result should be the same, right? There shouldn't be any difference. So when I joined UT Dallas, we conducted some research with our PhD student on privacy preserving decision trees, and also looking at how you can add more noise, such as perturbation methods and so on. So now we have this big data problem, right? That's what this conference is all about. And so with big data, data mining, security, privacy is exacerbated because you have now lots and lots of data that are being collected and analyzed. As a result, privacy could be violated. So I organized a workshop sponsored by the National Science Foundation in 2014 September, and presented the work to the Interagency Working Group in Washington, DC in February 2015. And quite a few efforts have been funded by various funding agencies since then on data privacy. Okay, so we had this workshop on big data management, security, and privacy. So what were some of our conclusions as a result of that workshop? So we know that due to technological advances and novel applications, we can now capture, process, analyze large amounts of data. And this data can be used for not just for medical healthcare applications, medical applications, financial applications, marketing, retail. It can also be used for security tasks, right? So it can be used for cybersecurity, such as authentication, access control, anomaly detection, and so on. So without a doubt, big data management and analytics is of tremendous use for a variety of applications. So as I said in the next bullet, by analyzing integrated data that's being collected, you can do homeland protection, disease outbreaks, and so many things. But there's a big problem. The more data you collect, even if you anonymize by removing the identifiers, you can link different pieces of data and be able to records and be able to re-identify the individuals. That's a challenge. So even security tasks like authentication, access control, they could require detailed information for multi-factor authentication. This information, if misused or stolen, can lead to privacy breaches. So some of the directions at the workshop: securing the data, access control models, privacy enhanced techniques, big data analytics for cybersecurity, and one other key area, which we really didn't address as much at the time. But as I said, that's one of the hottest area now in cybersecurity. And that's what happens if the machine learning techniques are attacked. Okay, so these were some of the discussions. Since that workshop, we started a project on privacy-aware quantified self. Quantified self is a movement by sociologists and psychologists to collect data and analyze the data and give advice to various people about better health and so on. Wouldn't it be great, like if I go to the refrigerator and open it, and I love chocolates and vanilla ice cream, so I start eating chocolate cake or trying to take chocolate cake out of some vanilla ice cream, and the system would tell me, no, you're not supposed to eat chocolate cake and vanilla ice cream. That would be great. But in order to do that, lots of information about me, about individuals, have to be collected, right? So quantified self on the one hand can give advice and improve health and personal habits, but this data is being shared with other service providers, cloud services, and so on. And the danger, such data collection and sharing, what happens is that it's being carried out without the user's knowledge. Okay, so a lot of danger, and personal data may be used for improper purposes. For example, data collected by a device monitoring blood glucose levels might be used by insurance companies to deny coverage, right? So that's a real concern, because let's say if I have a high blood glucose level, then my son might be denied insurance coverage. So such privacy violations could easily get out of control if data collectors can aggregate financial health related data with tweets, Facebook, and so on. And that could result in lawsuits, right? So to address these growing challenges, we need tools for privacy protection. So what are we doing? So we are proposing a privacy-aware quantified self-data management framework. And what we are saying, policies have to guide everything, because all of the data for quantified self, health information, fitness data, location data, social media data, image, video, other data sources, all being collected on our smartphone. Data collection, data storage, data analytics, data sharing. All of that is carried out, but some data could go into the storage, some cloud-based services. But what we are saying is every process here, data collection or data storage, data analytics, it has to be guided by policies. Okay, policies have to specify what data to collect and what data not to collect. Okay, and what data to store in the cloud storage and so on. So policies are a key aspect. So what do we mean? This is sort of what's in our mobile device, and then cloud-based encryption. So as more data is collected, the storage on the device will not be sufficient to store all of the data. So what we are saying is some of the data could be encrypted, some may be not encrypted in the cloud. But again, the access control policies, right? Based on those policies, local apps running on the device will give access to some of the collected data. When needed, these apps will be allowed to access some of the encrypted data. So everything is according to policies. Policies could also say that maybe you don't need to have fine-grained data, like you don't need to store a 20-year-old's weight every day. But a 70-year-old's weight might have to be monitored every day, right? So in other cases, the data will have to be deleted to preserve privacy. And what happens when the data is deleted? Say data deleted in the cloud. Is the cloud really going to delete the data? You may have to do an audit. We envision that data sharing analytics will be carried out using services in the cloud. But here again, what sort of policies govern that? Right? So based on different scenarios, some data could be sent without any modifications, some could be randomized, and so on. So that's policy aware. So we are not just working, developing policies ourselves, because we computer scientists, right? We develop technologies to enforce policies, specify policies, but we don't come up with the policies themselves. So again, we don't want toy policies like I mean, I tell a secret to John and tell John, okay, John, please don't tell Mary the secret. So that's not what we want. So we are working with policy expert. And so from our School of Policy, so she's sort of guiding this research by specifying appropriate policies. So that's one aspect of our research. So that's privacy aspects. Now comes data science for cybersecurity applications. Now, this sort of research started probably about 20 years ago, around the time I gave the presentation at IFIP conference in 1996. But at that time, data science was sort of what we called it data mining, which is sort of, because machine learning, AI was a little bit down at that time, a lot of discussions on data mining. And then after 2005, and especially after 2010, it's all about AI and machine learning. But in any case, data mining for cybersecurity, the data science models were fairly static. But now we are dealing with streaming. So essentially we use past data to build a model, predict the labels of future instances, helping decision making. That's the basic idea. And so we have to collect lots of, it becomes a big data because we want to look at intrusion detection, insider threat detection. But then lots and lots of data coming in from network traffic and so on. So data is arriving in streams, a continuous flow of data. And it's quite common, right? Financial data or network data to look at intrusions, massive amounts of data. But the key point here is the concepts are changing, because today it will say by Microsoft, tomorrow could be by Facebook, the next day could be by Google, right? Or then by Amazon. So there isn't really one concept. So concepts are changing. So what do? We build an ensemble of classification models, and then the models are continuously being evaluated, maybe with some human in the loop, but mostly the models work amongst themselves at the processes and do a voting and throw away the models, discard the models that are no longer useful, and then replace them with new models. So that's where we do sort of, in a way, real-time data mining. And then if there is attack traffic, we block and quarantine. Benign traffic, we store in a server. So this is our approach. And this is joint work also with Professor J.W. Hahn at University of Illinois, Urbana-Champaign. And so we have applied it to a number of variations of this number of cybersecurity applications. In particular, we've done quite a bit of work on insider threats. So insider threats are people who are really bad people pretending to be good people in an organization. It could also be humans, or what we are looking at is more processes, malicious processes in the system, right? So it could masquerade as very valid, systems like a compiler, or it could be a database, or it could be some part of a application. They will look very valid, but they are masquerading and collecting information and sending it to the attacker. So we have designed and developed an ensemble base. That's the ensemble based models, right? Stream mining, both for supervised learning and unsupervised learning. Supervised learning, we use support vector machine and one class support vector machine. Unsupervised learning, we are using a graph-based anomaly detection method, right? Each one has advantages, disadvantages. Unsupervised learning is sort of more, it's sort of more practical, not practical in the sense more useful. And so this results in a classifier exhibiting a substantial increase in classification accuracy for data streams containing insider threat anomalies. And so we did insider threat and the architecture. By the way, there are some hands being raised, but what I would like is to finish my presentation, and then we'll spend some time answering questions, and I can also read the questions. So that's the main thing for me, to get this presentation over with, and then we can discuss questions. So this is our architecture. So we have various sort of system calls. We look at various patterns, and so we have I chunks, and then we take the data, extract features, and the key part is our stream-based classification and the ensemble of models number of algorithms, how they vote, and then disqualify or throw away the models that are no longer in use, and then replace them with models that provide the correct concepts, right? That can determine the correct concepts. So our algorithms, as I said, support vector machine, one class support vector machine, and GBAD, graph-based anomaly detection. And then these models are continuously being updated. And when the I+1 chunk arrives, then of course we do the testing and see whether it's an anomaly or not. So we published a number of papers, and also we have a book that we published probably around 2.5 years ago. And that was on big data analytics with applications in insider threat detection. Some of it was based on this particular work. Okay, so this sort of finishes the second part, our second topic, which is machine learning data science applied to cybersecurity. Okay, but now comes the more challenging part. As I said, one of the more critical areas right now in cybersecurity. What happens if the machine learning techniques are attacked? Adversarial machine learning. Adversary is modifying the data. So the adversary is there watching over what we are doing. Okay, so trying to learn what are the models we are using and what's the data we are using. So it's trying to thwart our activity. So we've got to understand what the adversary is up to. So adversarial machine learning is not concept drift. It's not online learning. It's just that the adversary is adapting to avoid being detected during training time, like data poisoning, during testing time, modifying features. So essentially there's a game being played between us and the adversary. So see what happens. This is, for instance, a support vector machine boundary. The red squares are bad instances, the blue circles are good instances. And so what the adversary is trying to do, learn what we are doing, and there. It's trying to push the red squares into near the blue circles so that they won't be caught. So because it has learned what we are doing. So now what we have to do is learn how the adversary has adapted, and then we've got to come up with an adversarial support vector machine. So what do we do? So we have to, first of all, we have to find out what are the attacks. The one thing is that instead of randomly developing solutions, we've got to find out what is the adversarial attack? What is the attack model? So our KDD, Knowledge Discovery and Database paper, we presented this work. And we talk about two classes of attacks. One is free range attacks, where adversary can move malicious data anywhere in the domain. I won't go into all this math. The other model is sort of a targeted attack. It is more challenging. And so we only looked at two classes of attacks. Remember, in theory, the adversary can look at any type of attacks, right? So that's a challenge that we cybersecurity researchers have. The enemy, all they have to find is one tiny loophole and get in. We've got to cover all bases. So here is our approach. So what we do, this is a support vector machine boundary. What we have done, so green circles here are good instances. The red crosses are bad instances. So we study how the adversary is adapting. And so we try to push this dashed line here. So blue line. Black dashed line is a standard support vector machine. The blue line is the adversarial, the new boundary. By pushing the new boundary, some of the red crosses are being caught. And so that's what we do here, right? We have the blue boundary. And so we are catching more attacks by moving it. Of course, you can ask the question, what happens if we can move it right here? Then we can catch all the attacks. But if we move this too far, all the good instances will show as bad instances. So we are going to have false positives, right? We don't want false positives, nor do we want false negatives. So the challenge for us, and the whole paper is a lot of mathematics involved and game theory, is to find the appropriate boundary for this support vector machine. So remember, this is just one example, right? For adversarial machine learning, and we look at adversarial support vector machines. Since we published our paper, there's been a lot of work on adversarial decision trees, adversarial neural networks, adversarial machine, various types of machine learning, you add adversarial onto it, but it's not straightforward. There's a lot of work that has to happen in order to find the exact boundary. Okay, so that finishes my part 1. Part 2 is another topic, security and privacy for Internet of Transportation and critical infrastructures. And then I'm going to try and combine part 1 and part 2. And the part 3 is what we are really focusing, a lot of our research is focusing. Okay, what is Internet of Transportation? We all know Internet of Things. I looked at the program and found that there are quite a few on IoT and big data. And so a number of very interesting topics have been discussed at this conference. So Internet of Transportation, Internet of Things is like our phones connected to our televisions, to our refrigerators, to our lights, and so on. And same thing, it's the Internet of Things for transportation. So here we have the cars are all connected, and the trains are connected to the cars, and the trucks are connected. And here we have roadworks all connected. So it's really, really becoming a huge industry. So Internet of Transportation, major implications in the transportation industry, autonomous vehicles, AVs aim at improving day-to-day activities, helping us with our driving, improving traffic, transportation of goods. It's estimated 63% of the freight goods or the US trucks carry an estimated 63.3% of the goods. AVs are not limited to ground vehicles, right? We can also have aerial and sea vehicles, although our experiments have only been with aerial and ground, because we don't have any ocean here, with a wide range, or we have some lakes, but we don't, we just decided to do with ground vehicles and aerial vehicles, wide range of applications, levels of automation for AVs from 0 to 5. And we find that ground vehicles is only partial automation, level 2, whereas aerial vehicles have a level 4 automation. And companies like GM have spending huge amounts on Internet of Transportation, $728 million just in 2018, and they said 2019 is $1 billion. It'll be very interesting to get the figures, what they did for 2019 and 2020 as well, because 2020 is almost ending. While there's great potential in AVs, of course, a big problem, right? Security and privacy concerns. So what have we done? Before that, security of autonomous vehicles, AVs evaluate their environments using a variety of sensors, camera, GPS, inertial measurements units, LIDAR, radar, and ultrasonic sensors. And prior research, some of our research has shown that sensors are susceptible to malicious tampering. Example, IM used to susceptible to sound waves, and GPS receptors are susceptible to spoofing signals. So vehicles should verify the veracity of the signals before acting. So sensor-based AVs rely on sensors to evaluate and interact with the environment. And some of the problems, sensors are susceptible, as we said, to GPS spoofing, transduction attacks, manipulate environmental physical signals. Classical computing like operating system security, memory management, and so on, not sufficient, right? They are not enough. And they don't protect against these types of attacks. And then there's also no verification, because real-time constraints, AVs trust and act upon sensor data without any form of verification. So this becomes a really challenging problem. What did we do? So we looked at the physics of the properties, right? Physics of the control systems. So my colleague, Dr. Cardenas, is an expert in control systems and security. So he was quite influential in coming up with the design together with a student. So we built a reference monitor. For those of you not familiar with security, reference monitor is that part of the system must be security critical. It performs the most critical security operations. And we want to make it as small as possible, right? Because we don't want the reference monitor to be attacked. So we used a physics-based anomaly detection, PBAD, for ground and aerial vehicles, because as I said, we didn't do C. The algorithm has 3 parts. It might sound simple, but it's a lot of work involved to get these physical model, building a model offline, right, physics-based, and then implementing an online tool to monitor expected and observed behavior. That's we use just extended Kalman filters, and then raise an alarm if significant residual difference exists between executions. That's our anomaly detection part. And so our design, here is our physics-based design, the model, and you have various parameters like moments of inertia, mass of vehicles, drag factor, thrust factor, and so on. And offline processing, the AV's invariants are calculated based on the physical calculations using well-known linear model for aerial and ground vehicles. Accelerometer, gyroscope, and magnetometer sensor data on the X, Y, and Z axis for the aerial vehicle, and vehicle positioning steering angle for the ground vehicle. Online stage, we used extended Kalman filter that's been around for a long time, so no fancy machine learning here, is used to predict AV's physical behavior by estimating unknown parameters from noisy sensor input. The algorithm is divided into two sections that predicts and corrects estimation before it's compared against the sensor data. So once we set the stage, then we go into anomaly detection. And again, there's an algorithm in the literature called CUSUM, C-U-S-U-M, is then used to detect persistent attacks. So an alarm is raised if the residual difference is larger than a predefined threshold. And the paper was presented actually at the Usenet Securities, one of the top 4 cybersecurity conferences. Okay. The physical implementation, of course, we used drones. That's because we don't have airplanes. Drones, aerial AV Intel ready-to-fly drone controller is PX4 flight controller focused on detecting GPS spoofing and gyroscope attacks. GPS attacks are detected after 0.2 seconds, while gyroscope attacks after 1.5 seconds, and overhead is about 5.4%. For ground vehicles, we used a custom built on top of Traxi Ford Fiesta ST Rally Cheshire. Controller is ROS Kinetic Cam, focused on detecting visual attacks. Remember, camera visual attacks detected after 0.1 second, and overhead introduced 2.25%. Each threshold produces a probability of false alarms of approximately 2%. Okay, so since we finished this paper, we've also done some additional research about how the cars and trucks driving together in a swarm, right? How those attacks could happen and what happens if one system is attacked and how are the attacks propagating. So we have submitted a paper and waiting to get the results at the ACM CODASPI, the Data Security and Privacy Conference. Okay, and then of course, privacy is very critical, right? Beyond the security of individual vehicles, and transportation sector could greatly benefit from a supporting infrastructure for privacy, right? Because what happens is that there's a lot of motion sensors on lampposts, surveillance cameras to help identify traffic jams. So without a doubt, a lot of this surveillance technology is very useful, right? To catch thieves and if there are road accidents and so on, who was at fault, very good. But from a user perspective, the privacy concerns arise from all the information needed by such a system. That could lead to private information being exposed, such as vehicle identification and driving patterns, right? So these are some of the big problems that we have. So legislators, engineers, scientists should keep privacy concerns in mind as advances in IoT become more prominent in day-to-day activities. This will aid at improving public perception, reduce hesitation from consumers, and increase the adoption rate of new technologies. Another thing with respect to privacy is that, you know, I may be smoking. Well, of course I don't smoke, but let's say I smoke. I don't want anyone to see that I'm smoking when I'm in the car, because if that information goes to my healthcare providers, they are going to increase my premium, right? So that's one thing. And another thing is my driving patterns, right? I don't want people to, you know, surveillance cameras to find out what my driving patterns and send it to my insurance company, driving insurance company, and then they will look at my driving patterns and, you know, increase my premiums. So certain things, and also I don't want that I'm, you know, in a certain location. I don't want anyone else to know. So all of this becomes very important. But so far, we are so concerned about surveillance in the sense that we need to catch the people, you know, drunk drivers and people who are causing accidents. That's important too. So there is always this sort of the sort of trade-offs, a dichotomy between security, because for surveillance is carried out for security, and privacy. Okay, so again, it is not just one or the other. It has to be sort of trade-offs, a range, a quality of service, what type of service. Sometimes security is critical, sometimes privacy is important. So that has to be a trade-off. And not much has been done in this area with respect to privacy. Okay, so that's where I think we have a challenge. Okay, so I have, it's about, right, so 9:06, so your time is 3:06. So I'll talk for another 10 minutes and then we can have a discussion, okay? So application of SEC AI for Internet of Transportation and Infrastructures. So that's applying the first area, part 1, to part 2. So we get part 3. So this is really where our research project is right now. Data science AI for transportation security. Remember the algorithms that we said for the attacks to the GPS and to IMAs. So those attacks, we use sort of Kalman filters and the Kusum algorithm. We didn't bring in data science and machine learning. So Internet of Transportation subject to attack like any other cyber physical system. Streaming data is being collected from such systems, including autonomous and in the future driverless vehicles. As transportation systems go electric, of course, we need energy conservation. So threats to security system, it could cause havoc, right? A massive damage, including accidents, loss of lives, and so on. We could be stranded on lonely highways due to attacks on energy management. Data science ML techniques are being applied to analyze the data. So that's my part 1, right? We talked about data streams. That streaming data can be applied to analyze what? Telecommunications security, or even financial data to tell us which stocks to buy. So lot of applications. Now, can we apply the stream mining techniques or stream analytics that I mentioned? Can we apply that to transportation data to detect security violations? Or can we insert that into our Kalman filter, the physics-based anomaly detection? Can we somehow or other bring in the machine learning to give us better accuracy, right? Because the algorithms that we have used, right, it's not looking at, say, the concepts that are changing, right? In the part 2, we are just looking at, is it an attack or not? We are not looking at concept change, everything that is changing. So concept evolution, no, we are not looking at that. So can we bring in? So the main question, we believe, is to understand the nature of the complex transportation data and adapt the stream analytics techniques and apply them on the massive amounts of heterogeneous sensor data. So that's sort of we are looking at bringing in the data science and the transportation and the Kalman filters and the Kusum algorithm and so on. Can we integrate it? That's data science. The second area is this adversarial machine learning, right? That's one of the most important areas, as I said, in cybersecurity. So can we build sort of Internet of Transportation systems? Of course, without a doubt, these systems are going to rely on data science and machine learning, because that's going to help us to have better driving and tell us, maybe you should take this particular route, or what sort of instructions, and, your gas is, you are low on gas, but that's of course fairly straightforward. We still have it. We don't need sophisticated AI techniques, but we are lost. It can give us directions, so many things. So without a doubt, AI ML is very important for transportation systems. But those data science AI ML techniques could be attacked because the adversary is learning the AI techniques that we are using, right, for our vehicles. And so learning about the data used to train the models. Adversary will attempt to thwart the vehicle's learning process, right? So what happens if it can attack our machine learning? It could cause a lot of problems. Therefore, the learning algorithms have to adapt to thwart the adversary's actions. Eventually, it becomes game playing. So that's what happens. So one point, the adversary could also attack our extended Kalman filter technique, right? Or whatever machine learning we put in there. What if those Kalman filter techniques themselves are attacked? Then of course we cannot rely on the results, right? So healthcare data, if it's attacked, then we cannot provide good medicine. Financial data is attacked, then financial analysis is attacked, then it can cause, real chaos in the financial world. So anyway, eventually it becomes game playing between the adversary and the vehicle's machine learning algorithms. The challenge: what sort of game will be played? Is it zero sum? Is it Bayesian game? Is it Stackelberg game? So we really need to understand the type of sensor data we are dealing with. And research on this topic is only beginning. Next comes the privacy-aware, policy-based data management framework for Internet of Transportation. Remember, I had another picture earlier which showed our smartphone with data collection, data storage, and data analytics, and so on, right? And so now we have not that. Now we have in our car some sort of gadget that's going to have all of this collection processes. And what's the data? Not healthcare, social media data. It's radar, GPS, cameras, LIDAR, ultrasonic sensors, some of the data encrypted and goes into cloud storage, and some other data anonymized and goes into cloud-based services to provide some services. So this is the privacy-aware, policy-based autonomous vehicle. So what sort of data should we collect? How do we store and access the data? What sort of analysis should we perform? How do we share the data? Different cars are going to share the data, right? Vehicles. So should we openly share everything, right? So what we are saying is policies have to guide what data is being collected, stored, and analyzed and shared. We have not done any work in this area yet, because as I said, privacy is something that's just, research is only just beginning, even without coming up with this sort of fancy privacy-aware policy-based framework. But eventually, I believe that this is the direction that we need to take. But then one concern is that we may have so many policies that implementing them could be very, very difficult, right? Complex. So there's a trade-off between all of these, privacy and security and so on. So that's what we need to keep in mind. Okay. So I have just got about two more charts, or three more charts. Okay, so there's this whole area that's emerging called trustworthy analytics. So remember what I'm saying is that the machine learning techniques, going back, the machine learning techniques could be attacked. Is there some way we can carry out machine learning so that they are not attacked? So again, computations over big data may require massive computational resources, and organizations may use a third-party service to outsource some computations to be cost-effective. So when these third-party servers are used, data inherently becomes available in untrusted environments, either observed by man in the middle during data transmission or inside a threat. We talked about it, right? Adversaries at the third-party location. In these cases, the data owners may need to protect their data and require cryptographic guarantees about data security and integrity of computational output from these third-party services. So how do we provide trustworthy analytics, right? So one good news is that Intel has come up with SGX, the Intel chip, and it supports trusted execution environments. So we are conducting a lot of research on using research in secure encrypted stream data processing and trustworthy analytics, and using advancements in embedded hardware. Okay, so some are saying that securities, and I'll talk a little bit about it later, which is what's really concerning me. But anyway, let's do more stuff in hardware, and that way, we don't have to worry as much about security, but hardware could also be attacked, right? But again, software in a way is more vulnerable. So we have to explore this for Internet of Transportation as well. But one thing to note here is that there are some articles that have been written about the Intel SGX processor, that it might not be as secure as we had thought, but I need to understand more about what the issues are. So at least at this time, we've done a lot of work, and it seems to have a lot of promise. That's all I can say at this time. So what does this SGX platform look like? So it's SGX enabled data analytics. So we have all these users with secure connection, and then you have application memory, runtime, and various wrappers, and then you have the encrypted code and the encrypted data. And then you have the various enclaves that can perform data analytics, right? So this is, and then there's a global attestation between the different servers. So this is what we architected to carry out analytics in a trustworthy fashion. Now, is this going to solve our problem? We still need more work to do before we can, we can sort of make this assertion that this is the solution for sure. Okay, so that's where we are right now. Now, my last chart, and I also want to leave you with a few thoughts that are going to be really concerning. Okay, so let me finish the summary first and then talk about what the danger, that the potential danger we have. Of course, developments in AI, security and AI, integrating cybersecurity and artificial intelligence exploding. Applications of AI for security, insider threat detection, many other applications, malware analysis, and security for AI, adversarial machine learning. Also developments in privacy-aware healthcare and managing one's life's activities, right? So without a doubt, quantified self is helping people, but we need to protect the privacy, right? So we need to come up with a privacy-aware policy. So we are saying policies have to guide everything. At the same time, with the development of the Internet of Things, Internet of Transportation Systems and Infrastructures, security and privacy solutions are being developed. And as I explained, our solutions are mainly physics-based solutions using Kalman filters and so on. As driverless cars become a reality, more and more of the AVs will use AI machine learning techniques. How can we develop AI solutions for detecting malware in autonomous vehicles? And also, what happens if these machine learning techniques are attacked? Machine learning techniques we are applying to autonomous vehicle systems are attacked. So can trustworthy analytics help us with the solutions? But before that, can we develop a privacy-aware policy-based data management framework for vehicles, Internet of Transportation? And how useful will trustworthy analytics, the Intel SGX platform will be to carry out this trustworthy analytics? So this is a topic, numerous opportunities for substantial research. What I have mentioned here, even the third part could be enough for about 3 PhD theses, just the third part. Okay, so one thing I want to leave you with, I mean, so recently I was talking about quantum, that's not my area, by the way, but I teach a course on big data security and privacy. So we just finished, it's funded by NSF, and to prepare all the course materials. So we just finished the semester. And so my last lecture, I was talking about various technologies, right? The future. Of course, now quantum computing is very real, right? So we heard last year, Google said that they've got, very sophisticated machines, and then some Chinese government or some company in China said that they have, conquered, quantum computing. So this is very real. And quantum computing can do calculations much, much, much faster than the machines, the fastest supercomputers we have today. So what has happened is that today we are using, for encryption, AES 256 bits, right? Encryption. So that has not been broken yet. And what we are hearing is, based on studies, it's going to take millions of years to break that code, 256-bit encryption, or very, very long time. So they are saying with quantum computing, 2048 bits, right? So 256, 512, 2000, 124, 2000, 2048 bit encryption can be decrypted in milliseconds with quantum computing, whereas with traditional computers, it's going to take trillions of years, okay, to decrypt this fastest computers. So quantum computing is going to completely, if it works, going to decimate encryption. So what are we going to do for security, right, for encryption? And so researchers are looking at some sort of lattice-based encryption, right? So, but the one, okay, so there's also quantum cryptography, which is a different thing, because current crypto systems use mathematics, right? A 0 or a 1. But quantum cryptography uses physics-based encryption, right? So it's the minutest subatomic levels, so the photons. So the one thing which is not good, in the sense that it's very, quantum computers are a bit unstable now, because they have to be, computations have to be carried out in deep space. It has to be really, really freezing cold, deep, like temperatures of deep space. So, and slightest perturbation, variation of temperatures, you can't get accurate results, because it's not just 0 or 1, you could have 0 and 1 and straddle both. So because of the complexity, the computations today, quantum computing is not reliable. But if they make it reliable, there are some papers that are saying that even quantum computing can break quantum cryptography. So that's going to be a huge problem. But another thing, it's really expensive to develop a quantum computer, because you've got under the conditions under which it has to carry out the computations. So only rich states can afford to do quantum computing, or very, very, very wealthy companies. So just individual like myself will not be able to do quantum computing, right? So, or not use quantum computing. So but without a doubt, quantum computing is going to be very useful for big data, because we are collecting 2.5 exabytes of data a day. So imagine, with all of this data being collected, quantum computing is going to be really wonderful, solve the big data problem, right? And machine learning, right? It can operate on an AI, massive amounts of data very quickly, but it's going to be very dangerous for cybersecurity. So hopefully those of you here, the younger generation, the bright ones, can develop solutions. While we develop, that doesn't mean we don't want quantum computing. So while we develop quantum computing, there's also going to be massive, more and more data being collected and analyzed. And yes, we also have to come up with viable cybersecurity solutions. So that is the end of my presentation. And I'm going to stop sharing. And there were some questions. So there was one person who saw her hand up, and I didn't, oh gosh, all these news things.
Thank you for your presentation. It was a really interesting and very kind of really broad, from basically having hardware implementation to basically being policy aware. So this is fantastic. Thank you so much. So please do ask your question, raise a hand, or post it in the Q&A. And if I may, can I ask the first question? Can I be
Sure, please do. Please do.
So you mentioned trustworthiness, but
Yes.
you probably mean the trustworthiness from the system perspective. So this year especially, something came up, I mean, we've all experienced, is the trust of technology from the user perspective. And two particular things that were discussed with many of the contact tracing applications and so forth is basically giving the user the transparency to know where the data is and having control over it. And so in that sense, how do you see, is it possible using the encrypted methods that you describe, encryption and then basically anonymization, and does it allow for this type of control for the user to be able to be controlling and being aware of it?
Okay, so that's a very good question. Trust is that, so when we are, as a cybersecurity researcher, say I'm 50% data science, 50% cybersecurity. So as a cybersecurity researcher and privacy, what is most important for them is the security and also the privacy. So to get the privacy, you may have to perturb the data, right? You may have to modify the data a little bit, anonymize. So accuracy might have to be, accuracy might suffer, right? When you have when you have to really be concerned about privacy. And with respect to security, sometimes you might want to masquerade stuff. So there is a little bit of, integrity issues, integrity versus security, right? Integrity versus privacy. From a user's perspective, you want the data to be accurate. And again, with contract tracing and so on, right? So actually, tomorrow I give a keynote at the big cyber conference. And so there I'm going to connect with the COVID-19 and the privacy and contact tracing. Those are the things I'm going to discuss. So yes, so there is it's well known that there is a sort of a trade-off between security and privacy, security and accuracy, data accuracy, integrity, privacy. So it has to be sort of like a quality of service. So from a user point of view, when we talk about trust, we trust systems. Are the users trustworthy? Is the data trustworthy? So your question is more, how do we trust the data? How do we trust the system? So you need to put checks and balances like formal verification techniques. That's why you go into verification for systems and software. But from a data point of view, there is this whole area called data provenance. Data provenance is keeping, as we've done some work, keeping track of the history of the data and to see when was it anonymized, what happened to the data. So then you know where the data could have gotten corrupted, either maliciously or genuinely because of, trying to add and perturb the results. So today, encryption, especially with 256-bit encryption, we can sort of guarantee security in terms of confidentiality, right? Because it hasn't been broken so far. But that only provides confidentiality. It doesn't provide us with support for, for ransomware and so on, right? So again, to answer the question, there are various things. The verification, you have data verification, look at provenance and keep track. And again, technology to help that. But again, how do you trust the technology, right? So it's always that sort of dilemma. So that's a very good question.
Yeah, thank you. Yeah, it's not obvious. So Omar, you have a question.
Yeah, so thank you so much for that fascinating talk. So I just had a question about machine learning models. So in a typical machine learning model, for example, a deep learning model, you could have a very large number of potential parameters. These are weights or learning rate, momentum. This could be hyperparameters. Yeah. So how do you differentiate perhaps between an attack and noise within your model? Because an attacker could just pretend that it's noise, but in fact, it could be potentially an attack that is happening during the learning process.
Right. So what we are doing now, but that's a very good question. So in the future, maybe we had to look at the noise. Okay, the noise could be maybe a different type of pattern for the noise versus the attacker's pattern. But now what we are looking at, anything that is sort of deviates from sort of the normal, even when noise could be considered as an attack, and then we go and analyze it further. So with deep learning, right, several layers of learning where you can discard it and noise. It could be noise or it could be attacks, and then we have to re-look at it in several layers, right? So that's what we are doing now. But I think in the future, with deep learning and bringing in multiple layers of learning, you can maybe go step by step and throw away noise and do some analysis, multiple analysis. So attacker you can think it's a noise, but you have to still check the noise. But as you said, the attacker can put in noise and then it can sort of masquerade itself. So we have to then check also the noise. And so that's a good question. So essentially, how do you separate the noise from the attacks? There is some work that's being done in that area right now. But again, we need to, as we make progress with machine learning, this particular problem, I believe, we'll have a better handle on the problem.
Thank you. Thank you very much. Thank you.
Thank you. So any more questions, please?
There was someone who had raised the hand earlier.
Yeah, there was some. Your discussion on quantum computing was kind of like really interesting. So that's true. So yeah,
Right.
in
So
that
that's the challenge, I think, for the future. I mean, I'm really worried because they are saying 2023, they are predicting that these quantum computers would be perfected. And once that happens, I don't know what's going to happen to security.
well, the moment it's expensive. So to have even a 1 qubit installed, I mean, it's very expensive.
It's very expensive, but then the nation states will, everybody will be looking at what the other person is doing. So that's going to be a very dangerous situation, right?
Everybody will just buy one. So
right, that's the thing. So country A can know what country B is doing, B knows what A is doing. So everybody knows what their secrets, other person's secrets are. So that should be a very interesting time.
indeed.
And then, of course, is Internet of Transportation. So that could be a big, huge research topic. So I'm hoping that, this presentation, the whole idea was to, it was a broad presentation. Each one could have been an own presentation. So it was fairly broad. So each, especially the third, part 3 that I mentioned, that could be, as I said, several PhD theses. So that's what we are working on right now, or what are the areas we're focusing.
So when you say transportation, I mean, you mean only Earth-based transportation.
We also do drones. Remember, we have done drones. Transportation could be, right now, our focus is aerial vehicles and drones as well. But this is going to be autonomous vehicles, is not just ground, it's aerial, and it's also sea.
So
land, all the ships have to be coordinated, ships and boats, and then all the airplanes and drones have to be coordinated. And then, of course, the cars and the trucks and the trains, that's what I call about ground vehicles. So and they all have to be coordinated.
What if we go beyond that and go into space?
Space, right. I didn't, that's a good point. Space, right now we have got space service, right? Air Force, Space Force, right? I don't know how far they have gone with Space Force. But yes, if you have several rockets flying around or unidentified UFOs, but it may seem very far-fetched right now, but it could be very real. All of these things going around, and it could be in the future, right? It could be, all of this could be very real. So
yeah, with ongoing projects such as Starlink and so
right.
on there.
Another thing we talked about, quantum computing could be very useful to handle massive amounts of data to detect these attacks, or the previous question, whether there's noise versus attacks and so on. Very quickly it will be able to detect. So it can be used for security. But again, it can break all the encryption code. So that's the biggest challenge. So I think I've sort of gone over my time. Thank you. Anyway, thank you very much.
Thank you so much. Thank you. So do we have any last questions? Anybody wants to? Okay.
I got some good idea from the question from Omran because of the noise, and that was something that I really want to think more about what you have said. So I think both of you all have given me some very good ideas about the data trustworthiness, the main question, the data trustworthiness, and separating noise from the attacks.
Thank you. This was a really good, interesting presentation. And again, I would like to thank you again.
Thank you so much for inviting me. I really, and I'm really pleased it's IEEE ACM joint, since I'm a fellow of both ACM and IEEE. So my loyalty is to both organizations. And this is really great that both have joined together.